Good morning. It is my great pleasure to welcome you all to the Library of Tibetan Works and Archive. A special thanks to all the distinguished guests from various organizations. Thank you all for being present here today. It is a great honor for the library to welcome Professor Michel, who has accepted our Director Geshe Lagdola's invitation. Professor Michel is the Director of National Center for Science and Research in Paris. He's also a researcher, a scientist, and a writer. Besides many books, his book on quantum mechanics in French language was recognized and has received an award from the Academy of Moral and Political Sciences from France. He's also a long-term interest in the philosophy of Madhyamika school of Buddhism and has participated in 2002-03 Mind and Life Conference, which is a dialogue between science and Buddhism. He's also was a speaker during the 2013 Mind and Life Conference, which was held in Mongod in South India. And today he's here, and he'll be doing this 3-day lecture series. I hope, and I'm sure, that this lecture series will be of great interest and an enlightening one for all the participants here, and will be really an instrumental in promoting peace, harmony, and well-being of all sentient beings. Welcome you all to LTWA. Thank you.
Thank you. It's really a pleasure and an honor also to be with you. You know that I've participated to several of these dialogues organized by the Mind and Life Institute between especially His Holiness and many scientists. And I was the philosopher there. I had the role of a philosopher, and my role was to bridge between the scientists and the Buddhist scholars through, I think, through also the Western philosophical tradition. But when I attended these dialogues, I had the feelings that something had to be made clear. What are, in fact, the two disciplines we are comparing? What is science exactly? What is Buddhism? And how does their aim converge? Is it possible to have such dialogue? Aren't the methods and aims of the two disciplines too different, perhaps, to have this dialogue? So I had to inquire, what is exactly the disciplines we are comparing? So, of course, I will not teach you what is Buddhism. This is not my role, but I will try to let you know what is science and to what extent it can be compared with Buddhism. Another of my concerns was that the words that were used during these dialogues were not perfectly the same when they were used by scientists, Western scientists on the one hand, and when they were used by Buddhist scholars on the other hand. For instance, the word knowledge. The word knowledge seems very clear, yet I think it has very different meanings according to whether you are a Western scientist and whether you are a Buddhist scholar. Knowledge for Western scientists means isolating something that can be treated as an object completely separated from the subject. It's very dualistic, you know. Instead, knowledge, vidya in Sanskrit, means something much more close to non-dual awareness. in Buddhism, and also, I think, in many traditions of Indian philosophy. So, a word like knowledge means something that is not exactly the same between the two traditions. Another word that means very different things, mind. What is mind? For cognitive scientists, modern cognitive scientists, mind means a system of performing operations on information retrieved from the senses and transformed in order to act onto the world. So it's a very abstract meaning, a meaning that has nothing to do with our feelings, with our, with our experience, with our consciousness, nothing. Instead, in Buddhism, when people speak of the mind is completely different. It's not only just a sort of mechanical system of mulling information. It's really something that is lived. And it's even the level of, even maybe a deeper level of consciousness. So, even the meaning of words is a little bit difficult to reconcile. So, my first talk will be about what is science and how can it be compared with the kind of knowledge that is obtained for instance, in Buddhist contemplation. Okay, I will speak of a little bit difficult issues here about philosophy, about the history of science, and all these notions maybe you don't have. I don't know you yet. But if there is anything that is difficult, that you cannot follow, that is you never have heard of, please ask and interrupt me. Okay? So it will be easier like that. Okay, so what is the purpose of science, first of all? Is the purpose of science to give a picture of nature? A picture of nature. This is very commonplace in the West, saying that science is meant to give us a faithful picture of nature as it is, independently of us. This is, almost a cliche in the West. You say that you want to obtain knowledge of nature. And what is knowledge of nature? It's giving a representation or a picture of it in symbols. And these symbols are given by science. And we call that a mirror of nature. Okay? As you see, this very idea is already full of preconceptions, because that means that nature is something out there, independently of us, and we must try to get a picture of it. Okay? As if, here again, we were separate from it. Object, subject, duality. Another possibility, which has been also considered in the West, but usually discarded, is that science gives a projection of our mind onto something we don't know. So we project something of us onto nature. Here again, there is some duality involved. We are here, nature is there, and we give a projection, okay? But maybe also science is something in between. Neither a faithful picture of nature, nor a projection of our mind, neither all given to objects, nor all given to subject, but maybe something in between, namely a sort of middle way between everything's object, everything is subject, Okay, let's see how you can conceive to give a picture of nature, how you can conceive to mirror nature. There are two versions of the mirror of nature. one is called realism and the other one is called empiricism. According to realism, by science, you want to give a faithful representation of something that is hidden from you, but that explains what appears, okay? You don't just want to describe what appears. You want to see the secrets of nature, what is beyond the appearances, and give a faithful representation of what nature is beyond appearances. Empiricism is more modest. It just wants to give a faithful summary of observed phenomena, of perceptions, of experimental results, and so on and so on. Just a summary, not more. Not trying to go beyond these appearances, because maybe there is no beyond, after all. It's a possibility. Who knows? Now, so you see how you can think of this idea of a picture of nature. Either a picture of something hidden behind the appearances, or just a picture of what you see, nothing more. Scientific realism is the dream of scientists, actually. I must say, scientific realism is not just one doctrine among many others. It's what scientists would like usually to achieve. They would like to know the secrets of nature, okay? But there are problems. There are many difficulties in scientific realism, and I will show you in further lectures that, for instance, quantum mechanics is very averse to scientific realism. It's very difficult, especially in quantum physics, to think of nature as something completely separate from us that we try to understand from outside. It's very difficult. So, in fact, even before the advent of quantum physics, many arguments have been given against the ideal of scientific realism. For instance, Karl Popper, the celebrated philosopher of science, German philosopher of science, he said, okay, let's see how science works. Science progresses by conjectures and refutations. That means you do a hypothesis, you attempt a hypothesis, and you derive the consequences of this hypothesis. Then you compare between the consequences of the hypothesis and the phenomena, the facts, what you observe. If it fits, okay, well, you keep the hypothesis. If it doesn't fit, then you think, oh, maybe I should revise my hypothesis. That's the way science works. And therefore, you never reach a final state of science. It's always progressing by way of hypothesis, tests, and then withdrawal of hypothesis, new hypothesis, and so on and so on. So at this stage, we cannot know that science has reached anything like a final stage. And there are good reasons to think that it will probably never reach such a final stage. Of course, about this, there are discussions. So the idea of Popper is that since our science works this way, namely by conjectures, refutations, hypotheses, tests, and so on, then he said our science is not knowledge. Is not knowledge. Imagine. It can never claim to have attained truth, because according to the standard vision of knowledge in the West, knowledge is just a set of true statements about the world. Okay? So if you can only have hypotheses, you never have absolute certainty, then, according to Popper, you cannot say that science is knowledge. Okay? You see that it's very harsh. It's very far from the cliché, the prejudice about science, what science is. Okay, but on the other hand, other philosophers of science who were very close to scientists said, okay, maybe there are difficulties with claiming that science reaches the truth about the world and that science gives a good picture of reality as it is independently of us. Maybe, but look, science has a tremendous success. It works. It transforms the world. It has computers, planes, and so on. It works. And so, according to Hilary Putnam, realism, he said, is the only philosophy that doesn't make the success of science a miracle. He said, if science works, maybe it's difficult to explain without thinking that science is getting the truth about the world. Now, is it true that truth and success are always connected? That's a question, okay? Let's accept, as Popper says, that science doesn't give us a definitive picture of what the world is. Then how can we explain that science is so successful? You see the problem. Okay? So this is probably our main problem during this talk. How can we explain the success of science without accepting that science is a faithful picture of reality? Okay, now we try to get a way towards sort of middle way conception of what science is. In the history of science, there has been retreat with the usual aim of scientific realism, namely giving a good and faithful picture of nature as it is independently of us. There has been retreat. For instance, according to Sir Isaac Newton, already in the 17th century, science, especially his science, namely what is called now Newtonian Mechanics or classical mechanics, his science was not meant to discover, for instance, the ultimate nature of gravitation, the ultimate reason why bodies fall when they are dropped. Okay? According to Newton, his science, namely classical mechanics, was just meant to organize phenomena as they are observed, just make connections between phenomena. What kind of connection? I will tell you, mathematical connections. Namely, you can have the value, for instance, of the position and the velocity of a body at a certain point, and you want to calculate what will be the velocity and the position of this very same body at a further time, at a later time. This is the kind of information classical mechanics, Newtonian mechanics, gives you, not more. Just connection between the position of a body at a certain time and position of the body at a later time. Nothing about nature. Nothing about the nature of nature, I would say. Nothing about the nature of gravitation. Just calculation, not more. So, according to Newton, science is about phenomena, about observed phenomena, not about the nature of nature. Okay? But what is a phenomenon? Now, what is a phenomenon? Since science is only about phenomena. A phenomenon is the byproduct of an interaction between what we want to know, say the moon or the earth or anything like that, and our instruments of observation. A telescope, our eyes also, very important, okay? So phenomenon is a byproduct of an interaction between what is to be known and the knower, namely us. In some way, phenomena are just in between the two, just in between the object to be known and the subject who wants to know. Phenomena are exactly at the middle of the process of knowledge. Now, Immanuel Kant was, as you know, and I will tell you more about him in a later talk, Immanuel Kant was a German philosopher of the 18th century, and he was very much inspired by what he knew about the scientific work of Isaac Newton. So just 1 century, than 1 century before him. Newton's Principia was in about 1680s, and Kant's work was between 1750 and 1790. So Immanuel Kant was thinking, what is the nature of science? Since the science is so successful and yet it doesn't disclose the nature of gravitation, the nature of bodies, the nature of anything. How is it that is so efficient? So this was Immanuel Kant's question. According to Kant, science is a quest for stable and intersubjectively acknowledged relations between phenomena. Okay? Science is not a disclosure of the nature of objects. Science is just a way to relate, to connect, to make relations between phenomena in such a way that this relation can be acknowledged by any subject whatsoever. Any human being who would look at these phenomena would say, oh yes, I agree with you. This is the phenomenon which is observed, and this is the connection it has with a former phenomenon. For instance, this is a connection this velocity and position of a body has with a former velocity and position of a body. Everyone agrees about that. Everyone agrees. Why? Because they observe. They do again and again the same observation and say, oh yes, Newton was right. This is exactly what we observe. We don't know anything about the nature of objects. We don't know anything about the nature of gravitation, but we know a lot about the connection of phenomena. Okay? And phenomena, what is a phenomenon according to Kant? I told you that already, but I can repeat it. Phenomena are relations between us and what we want to know. Okay? So now you know, you understand maybe the new picture of knowledge that emerged in the 18th century in Europe. Knowledge, scientific knowledge, is not about the intrinsic nature of things. Scientific knowledge is about the relations between phenomena. And phenomena are relations between what we want to know and ourselves. So it's relations throughout, relations everywhere. And I think here you already hear a connection with Buddhism. You know, own being is not the purpose of our knowledge. We want to know the interdependence between phenomena. And phenomena are the interdependence between us and what there is. So here again, we have a picture of knowledge that is coming much closer to Buddhism than the former picture of knowledge, which was inherited by, from Aristotle, Plato, and so on. Okay? But before we come there, we want to know more about the success of science. How is it that science is so successful, even though it doesn't really bear on the own being of things? How is it? Well, as I told you, scientific realism would like to say that science cannot be efficient if it doesn't give us a faithful picture of things as they are. But Kant said, no, it's not necessary. You don't need to have a faithful picture of things as they are in order to be efficient. Why? Because first of all, you must understand that this aim of giving a faithful picture of reality is not verifiable. You cannot be sure that you will ever have a faithful picture. Why? Let's read a little bit about Kant's thought. There is, he said in a book on logic, there is no way to compare knowledge with reality except if we know reality. But then what we compare with knowledge is another piece of knowledge, okay? If I want to know that my theory is a faithful picture of reality, then I have to compare this theory with another piece of knowledge, maybe an experimental piece of knowledge. But I don't compare my theory directly to reality, just my theory, which is a piece of knowledge, with experimentation, which is another piece of knowledge. And therefore, according to Kant, we compare knowledge with knowledge. And therefore, we cannot really reach to reality. And we are never sure that we are faithful. So realism is a dream, maybe, of certain scientists. Realism, that means that science can reach the truth about reality as it is independently of us. This realism is a dream, but it cannot be checked. It cannot be verified. So if there is no certainty about science being a faithful picture of reality, how it is that science is so successful? You know, this is a leitmotiv, because it's a real question. It's a very difficult question. According to Kant, Kant had an answer. And it's a very interesting answer that can be just reactualized, modernized, in order to catch the modern science. You know. According to Kant, science captures the general features of phenomena that are necessary for us to ensure, one, their reproducibility, namely that if we do an experiment again and again, the same phenomenon comes again and again. This is a first condition for a good science. You know, I've been a scientist, and I know how difficult it is to set an experiment in which you get reproducible results. Because results, sometimes, you know, the apparatus is no longer well set, and then you see different results, and you say, oh, how it is then that you have different results. Then you have to set again the apparatus so that once again you see the same result. When you see that you have a right procedure to retrieve again and again the same results, you say, oh, okay, this is a phenomenon that is reproducible and can be observed by everybody. And then you say this is an objective phenomenon. That's good. But it's not, you know, you have not reached the own nature of things by this. You just have reached a reproducible phenomenon. And you are very happy about that when you're a scientist. Second condition, that these, you know, features of phenomena are intersubjectively valid. Namely, that anyone seeing the same apparatus would see also the same phenomenon. For instance, I remember His Holiness was using a telescope one day when he was in Lhasa, and he, you know, he saw that the moon has mountains, shades, and so on. And he asked one of his senior lamas to come and see through the telescope. And the senior lama said, yes, you are right. There are mountains and shades on the moon. So, you know, this phenomenon is a phenomenon that can be shared with other human beings. And therefore, there is a criterion of intersubjective agreement about this. So if you have this reproducibility and intersubjective agreement, then you can say that your knowledge will be efficient across time, irrespective of the place in which you do science. It can be here in Dharamsala, it can be in Canada or anywhere. It will be the same kind of result, and irrespective of subjects. Whoever observes through the same type of apparatus will observe the same type of phenomena. So here is the criterion of success of science, not reaching the true, absolute truth about the own being of things, but just reaching universal agreement about propositions that are used to predict phenomena. That's it. Okay. There was a British philosopher, Harrison Pemberton, who went and met some Buddhist monks. And he did more or less what I am doing here, namely giving an exposition of Western philosophy, and especially Western philosophy of science, and tried to see what kind of agreement or disagreement there was with the Buddhist monks. And he saw that the theory of knowledge of Kant was amazingly relevant to the concerns of a Buddhist monk. Why? Because Kant accepted that science is not more than a kind of conventional knowledge or conventional truth, and yet this kind of conventional truth can be amazingly efficient because you reach some criteria of universal agreement about these phenomena among all the subjects that can use it. So every engineer in the world can use the same formula because they have reached agreement. And this is the secret of the success of science, not more. Okay? Another way to say similar things is to rely on Francisco Varela's theory of cognition. You know, cognition is not exactly like knowledge, because cognition means that we try to understand the way living organisms, not necessarily humans, but living organisms, can cope with their environment. They can use their environment in order to have food and avoid threats. And this treatment of the information they get from the environment is called their cognition. And according to the theory of enaction that was developed by Francisco Varela, knowledge is not a faithful image of nature as it is independently of us, nor a projection of our mind. It's just the expression of a fruitful interaction between us and nature. According to Francisco Varela, there is a kind of dance. It was his expression, a dance between the living organisms and nature in such a way that there co-emerges a system of mutual adaptation. Namely, the behaviors of the organism become adapted to their environment, and the environment is progressively modified in such a way that it adapts to the organisms. So there is mutual adaptation. There is mutual co-arising between the environment and the organism. And now you can easily understand the reason for the success of science in these terms, in terms of biological adaptation. Okay? When an organism, a living organism, is adapted to its environment, this doesn't mean that it has a faithful copy of the environment inside the brain. It just means that it has developed behaviors that have efficiency with respect to a state of the environment that it has itself been modified by the action of the organism. You know? For instance, when an organism acts, when a bee acts in a field of flowers, when a bee acts in the field of flowers, it takes some of the nectar of flowers in order to make honey. Okay? But by doing that, the bee is not just using the flower for its own purposes. It modifies the life of the flower, because when the bee goes from one flower to another, it transports pollens from one flower to another. Okay? And then the life of the flowers is modified by the bee, just as much as the life of the bee is modified by the flower. So there is co-arising of a new pattern of mutual adaptation from the interaction between the bee and the flowers. Okay? So it's exactly the way you can understand the efficiency of science. It's not that science passively takes, if you take a camera, click, and you take a picture of nature as it is, independently of a camera. It doesn't work this way. In fact, science intervenes, it acts, it makes experiments. You will see that later. And nature answers the questions that are raised by the experiments. So nature is modified just as much as we are modified by, our approach of nature. Here again, there is co-arising of what nature answers and what we ask to nature. So here again, you cannot say that there is just picturing of nature. You must say that the success of science is explained by the fact that there is a mutual adaptation between the knower and the known, a mutual co-arising of the knowledge and what is to be known. Okay? Here, there is an example. Living organisms, as I told you, are not a picture of nature. They are adapted to nature. Now, it's also interesting to see some history of the conception of science and some history of the conception, especially of physical theories. It's very interesting if you go from the past to now, to the present. It's interesting to see that, in fact, the more you go in time, the less you expect from science, the less you expect from physical theory. So it's very strange, because the more you go from the past to the present, the more science is efficient. Clearly, the efficiency of modern science has nothing to do with the efficiency of past science. For instance, in the 17th century, with, say, Newtonian mechanics, you could do basically two things, only two things. Make clocks, with gears, clocks, and pendulum, or calculate the trajectory of bullets with guns. So very little was done, and maybe a little bit of machines, machines for extracting water and so on and so on. Okay. Now, what you can do with modern science, namely quantum mechanics, relativity, and so on, is amazing. It's computers, it's GPS. So the amount of efficiency of modern science is hugely bigger than older science. And yet, strangely, the ambition of modern physical theories is much less than the ambition of past physical theories. So it sounds like a paradox. How can it be? Modern physical theories claim to know less than old physical theories. It's strange. But let's see a little bit how it happened. Aristotle Aristotle was a Greek philosopher and scientist of the 3rd, 4th century before our era. So 2,500 years ago about. According to him, science is a statement of first causes of things and essential properties of things. So this was the basis of the birth of Western science. But as you see, these aims of physical theory, according to Aristotle, are very, very ambitious and very far from Buddhism. Because according to Aristotle, there can be, every event has a cause. Okay? He accepted that as a Buddhist, I would say. Every event has a cause. But a Buddhist would say, there is no end to that. Okay? But Aristotle said there is an end to that, and there is the first cause of everything. And he said the first unmoved cause to any caused motion. Okay, and then, the Western thinkers of later centuries, for instance, Christian thinkers, thought, okay, what can be this first cause? And they said, God. First cause is God, okay? But the idea that there is a first cause almost, appeal to God. Instead, if you don't say there is a first cause, no need for God. Also, essential properties. Essential properties means properties that belongs essentially to that substance. It's the own being of the substance. Two words that are almost banished in Buddhism. Okay? Own being, there has been the criticism of own being, and substance means an enduring thing, a thing that is permanent. And here again, there is a strong criticism of permanence. So you see, Aristotle set the standards of Western science by appealing to first causes and enduring things and essential, namely, own being properties. But then, in later centuries, in the West, there was a criticism of that. So probably, this progressive criticism of the original conceptions of the Western science explain why nowadays it's much more easy to have dialogue. Okay? For instance, Descartes, René Descartes, the French philosopher, he said that we cannot claim to have a knowledge of essential properties and first causes. We just observe that there are collisions between bodies, and a collision of a body onto another body explains the motion of the other body. One body arrives, then collides with the other bodies, and the other body moves. That's the explanation. It's called a mechanical explanation. And René Descartes criticized Aristotle for his idea of first causes and essential properties and said, no, there is just the interplay of causes and effects by collision. So it's closer to Buddhism, I think. Closer, but not yet, exactly, because this is called the conception of efficient causes. And the efficient causes were criticized in a famous chapter of Mula Madhyama Kakarika by Nagarjuna. So it's yet an intermediate stage, I would say. Then Newton. Newton said, no, I cannot even say the mechanical reason of motion. For instance, when I take a body and leave it and it falls. Okay, what is the body that impinges on it and explains the motion of free fall? What is this? I cannot see it. There is no body. So, according to Newton, you should not stick to the purely mechanical explanation by collisions. You have just to formulate a mathematical formula that describes the fall of the body. Full stop. You don't try to explain anything. You just describe the phenomena by a mathematical formula. Okay? So you see that here the aim of the physical theory is lower than the two former conceptions. Newton's conception is more modest than Descartes or Aristotle. Okay? And here you can say, what was Newton advocating? He said he was advocating the idea that science is only about regularities of succession. When something happens, something else happens. When something doesn't happen, that something else doesn't happen. Maybe you hear something familiar here. I think this is familiar because it was a Buddhist text. I think it was Samkhya Nikaya, in which you find the idea of dependent arising. When something happens, this happens. When something doesn't happen, this doesn't happen. Nothing more. So lower ambition, more modest conception of science in Newton. And then you have the final, maybe not the final, but the present one, which was the conception of Niels Bohr. Niels Bohr, one of the creators of quantum mechanics, said that science is not even meant to describe phenomena. Why? Because phenomena are not yet existent. They are not existent without us, without our intervention. A phenomenon doesn't exist in itself. It doesn't have own being. Not even a phenomenon has own being. And therefore, what you can do with that is only predict that if we do something, then a certain phenomenon will appear with a certain probability. That's it. You don't even describe phenomena as they occur in themselves. So the ambition of physical theory, according to Bohr, are even lower than the ambition of physical theory according to Newton, Descartes, and Aristotle. And here we are now, at this stage in the present days, with a very, very modest claim from the physical theories and from science in general, at least when scientists are lucid, I must say, because some scientists are not exactly as lucid as that, as Bohr, for instance. But then you have a very modest claim of science and yet a very powerful capacity of transformation. That is the interesting fact and paradox of modern times. Now, let's come back again to the history. How was science, how did science appear? From what kind of processes and social forces did it appear? There was a famous philosopher and sociologist in Germany called Max Scheler, who tried to explain very cogently the birth of science. And he said science was born of the meeting of two people who usually didn't meet. And I think this is the secret of Europe for the birth of science. If I could say, why was science born just at that time, in the 17th century in Europe, not in other countries? Because, of course, there were versions of science, but not the same kind of science, not as theoretical and not as practical as the European science of the 17th century. So I think the event is that two kinds of people met. Who were these two kinds of people? Craftsmen, namely people who do things, who, they arrange machines and tools and so on the one hand, and what we call clerks, namely people who think, you would call them geshes maybe, or, okay, people who think about our condition, about the world, about, the purpose of our lives, and so on and so on. And the others, the craftsmen, do things. They try to make our lives easy by building houses, pumps or mills, and so on and so on. these two people met. And strangely, the meeting of them was fruitful. Why? Because, you know, the clerks gave hypotheses about the workings of nature that guided the craftsmen. They said, okay, we could try to make better tools by using the hypothesis of the people who think, you know. And on the other hand, the craftsmen made tools in order to test the hypothesis of the clerks or the thinkers, you know. And so there was an interplay between them. Theory, experiment, thinking and making, thinking and making. And with this interplay of thinking and making, modern science was born. So here are some examples. First of all, there is a very strong theoretical element in modern science. Very theoretical and inspired from Plato, who said that everything, the world was, you know, the very real nature of the world is pure ideas set maybe in some upper sky, upper heavens, and these pure ideas have the form of mathematical concepts. So it's very strange. I think for Buddhist ears, it's a very strange thought. Reality is not what we see, what we can smell and touch and so on. It's something that we can think. It's pure concepts. Pure concepts that were called ideas by Plato. And Galileo, the founder of one of the major branches of modern science, and especially modern physics, was inspired by Plato. Here is what Galileo said. We cannot understand the universe if we don't know the language and the characters in which it is written. It is written in a mathematical language, and the characters are triangles, circles, and geometrical figures. Okay? So that means that the very nature of the universe is mathematics. The truth of the universe is mathematics. So this, of course, believing that was a very strong incentive to use mathematics in order to predict phenomena. Okay? So maybe here again we can think of this amazing event that explains the onset of science in Europe in the 17th century. You know, the true thing that was done by these scientists was to use mathematics in order to construct machines, in order to check the theory, and in order also to transform the direct environment of mankind. But what they believed was very different. They didn't think that mathematics was just a tool to transform the environment. They thought that mathematics was a picture of what the universe is. You know, that's amazing. But the fact that they thought so, the fact that they thought that mathematics was a picture of what nature is, was an amazing push for them. It was maybe an illusion, but it was a driving force in order to apply mathematics to these tools. Okay? I think this is a very crucial point, because sometimes there is an exaggeration of the significance of mathematics in science. Many scientists, even nowadays, would say, yeah, mathematics gives you the truth about the world. Who knows? Maybe it's true, maybe it's not true. Well, we can discuss about that. But what is certain is that for a scientist, believing that is a push. Okay? Sometimes, even if it's an illusion, it can be a push. Now, here is, I told you that the birth of science in the 17th century was due to the meeting of craftsmen and thinkers, or people who do and people who think. Now, You know, the people who think finally tried to use the knowledge of craftsmen in order to test their theories. How did they do that? They did that by setting experiments that are already informed by the theory. For instance, here is an experiment done by Galileo in the 17th century. It's, it's a slope, and if you put a ball on the slope, then the ball will roll. And since the ball accelerates, it goes faster and faster, then the little bells that are on the path of the ball will ring one after another. Now, if you observe carefully this projection, you will see that the bells are situated not at the same distance from each other, but at an increased distance between each other. What does it mean? That means that Galileo was already predicting the result. He knew that the ball would accelerate at a certain rate that he had calculated by his mathematics, and that if the ball followed his law, then the ball would ring the bells exactly at regular times. Tick, ting, 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 okay? Even though the bells are more and more distant from each other, the bell will ring at regular times. So at a certain rate, I would say, Galileo introduced his theory, his mathematical theory, in the very fabric of the experiment. You know, the fabric of the experiment shows the mathematics of the theory. So this is the amazing intermingling between thinking and making, between theory and experiment, you know. And this, I think, is the secret of the birth of science. Now, Immanuel Kant was a philosopher, as I told you, German philosopher later, and he understood a lot about this. He was very clear-minded, and he understood the meaning of this connection between theory and practice in a single item, which is an experiment of this type. And he said that when Galileo rolled balls of a weight chosen by himself down an inclined plane, a new light dawned on all those who study nature. They understood that reason has insight only into what it itself produces according to its own design. Okay? That's very interesting. This sentence is very interesting. Reason has insight only into what it itself produces according to its own design. Reason, the reason of thinkers, have an insight only if they produce the machine that is able to test it. Okay? Reason is, so to speak, inscribed in the tool. Now, reason has to be instructed, the last sentence, reason has to be instructed by nature, not like a pupil who has recited whatever the teacher wants him to say, but like a judge who compels witnesses to answer the questions he puts to them. Okay, the standard pattern of science before Galileo was just comparing ideas, but ideas, abstract ideas, made by clerks, made by thinkers, with observations, unprepared observations. We see things, we observe things. Instead, but passively, we don't do something to observe things. Instead, from the birth of modern science, things were very different. The theories, the ideas, were no longer compared with observations. They were compared to experiments. Okay? Experiments means doing something in order to catch the process according to the patterns that are fixed by the theory, namely according to the patterns that are fixed by reason. So reason asks the question, and it receives an answer. But the answer has been preformed by it, you know? So things are very different. And I think here again, we will discuss later about the relations between science and Buddhism. But I think this is a major difference, but we will discuss. Maybe you have another idea. This way of using experience in an active way rather than in a passive way is very different. Now, let's think about how we discover theory. How is it that a theory is formulated? How do thinkers do in order to formulate a theory? But the first idea that comes to mind is just to say, okay, theory is just an extrapolation of the past towards the future. For instance, I've ever seen that when I make, I drop an item, it will fall. I don't do that because I think it's glass. I always see that, and therefore it will ever happen the same way. This is the first idea that comes. The fact that things have happened in the past means that they will happen the same in the future. And so you set a theory that says exactly that. That says, okay, the rules of the falling of future objects is the same as the rule of the falling of the past objects. Okay, this is a very weak form of formulation of theory. And also, we could say the very project of deriving future from the past is not very credible. Why? Because you have observed only a few phenomena. You have observed maybe 100 falls of objects. And then you want to predict that it will ever be produced this way. It will ever happen this way. And therefore, you predict things about not only 100, but about an infinite number of events. So it's not very credible because you deduce much more than you know. So how can we save a little bit of this process, very simple process of so-called induction, namely deriving the future from the past? First point is to accept that the propositions obtained by this process have no truth value. They are neither true nor false, but they are likely. Namely, when you know that things have fallen 100 times, it's quite likely that they will fall the same in the future time. So this is just likely, not more. We could say that these propositions have practical function. Namely, they help us to try to formulate ideas about the future, but they are not real knowledge of nature. They can serve as hypotheses. So the idea of Charles Sanders Peirce, an American philosopher of the 19th century, was to combine a little bit of all these processes. Induction for first, induction, which means inferring the future from the past. Deduction, that means inferring a consequence from a hypothesis. And try to combine it, and maybe if you combine it, you give a good idea of the process by which a theory, a new theory, is formulated. The purpose of what Peirce called abduction, which is a combination of induction and deduction, is to identify universal propositions from which the singular propositions corresponding to observed facts could be deduced. For instance, here is the process. We notice the surprising fact, F. For instance, you notice that Mars, the planet Mars, is going a little loop. Okay, we notice that by observing the sky. Okay, but we don't explain that. Why does Mars undergo a sort of loop across the sky? Now, we notice that if the universal proposition U were true, this fact would inevitably be observed. For instance, we accept, like Ptolemus in the ancient times, that Mars goes in circle around the Earth, but have a sort of epicycle. And that this epicycle around the cycle explains that sometimes Mars goes this way, sometimes it goes this way, and therefore it performs a loop. So here is an hypothesis. The hypothesis can allow us to deduce the facts, namely the loop of Mars. And therefore, we should maybe adopt the hypothesis. But now you notice that this process is a little bit weak. Why? Because the hypothesis that explains the fact is not unique. There are many other hypotheses that can be better from other point of view. For instance, the hypothesis of Ptolemus, who explained, so to speak, the strange loop of Mars on the sky, is weak because there are other facts that it doesn't explain. And moreover, it's explained by nothing. So we must be careful, and we must know that it's only a hypothesis. And maybe we can change hypothesis, and by improving our hypothesis, we can deduce more and more facts. So here is the process. You see that it's very back and forth. Hypothesis, test, hypothesis, test, hypothesis, deduction of effect, and test of the deduction against observed facts, and so on and so on. Then you have more and more facts to account for. And if the hypothesis doesn't account for all the facts but only one fact, then you want a better hypothesis, what is called a unifying hypothesis, and so on and so on. And here is how science progresses. And precisely, what we want from a good theory is certainly more than just deducing one effect or one fact. We want it to, as I told you, to unify predictions under a small number of hypotheses. It's called economy, or maybe beauty of theory. Because if a theory can derive lots of facts from only two hypotheses, it's elegant, it's beautiful. Also maybe I skip on the other conditions, but you can have predictions that no other theory would have done, yet testable by experiments. All the known theory have not done these predictions, but the new one has done these predictions, and these predictions are checked. So the new theory is better than the former one, because the former one had not done this prediction. For instance, you could say the prediction well, there are many predictions that can be done, but the prediction that two plates in vacuum, two metallic plates in vacuum, are pressed on one to the other. No classical theory can explain that or predict that. Why? Because there is nothing. In vacuum, there is nothing. So what can exert the pressure on the metallic plates? Only quantum field theory can predict that by appealing to what is called virtual particles. Not existent particles, but virtual particles. And virtual particles that are created and annihilated, so they are very impermanent, by the way, according to conditions of wave agreement between the two plates. So here is a prediction that could never have been done by any other theory than quantum field theory. But this one does the prediction. The prediction is checked and observed, and therefore this theory is retained as the best we have at the moment. There is, in modern physics especially, there is a weak mode of prediction, which is called probabilities. I think probabilities are not very familiar to Buddhists, because that means that, maybe I'm wrong, but the idea is that events can happen by chance with apparently no cause. So I remember when we discussed with His Holiness the Dalai Lama, he didn't like very much the idea that event might have no cause, of course. But here again, it's not a statement, it's just something that we can say about events that look like they happen without cause. Let's suppose that indeed these events look like they have no cause. They happen by chance. There can be an event here, an event here, an event there, without any rule, any apparent rule. So what can we do as scientists? Should we just renounce and say nothing and not try to predict? Scientists are not very happy when people say, yes, you should stop doing anything and not trying to explain or predict. They want to do something, and then they do something by using probabilities. Namely, they predict not the individual event, but they try to predict the statistical distribution of events. When there are many, many, many events, then the events distribute not in a completely, orderless way. They order themselves. So we can predict something on a mass of events, even though we cannot predict anything on a single event. This is probability. Now, what is the reason why we have to use probability? Is it because nature is completely unruly? Is it because nature is indeterminate? Namely, that events have truly no cause. Okay, so I remember here again a discussion between our Buddhist scholars and scientists, in which they said, no, we cannot accept that an event has intrinsically no cause. I said, well, science cannot prove that. It just says some events look like they don't have cause, but that cannot prove they have really no cause. Okay? So another reason is that we ignore causes, but just because we don't have enough knowledge. And in the future, we'll be able to know more and know the causes. And this was the idea of some founders of probabilities, in France especially, Laplace, who said, okay, in fact, if we were omniscient beings, then we would know the causes, but we are just human beings, and therefore we are limited and we don't know the causes. Okay. But there is another option, and I think this one is very interesting also, and can be the right one for quantum mechanics, is the idea of a necessary ignorance of causes. Why? Why shouldn't we necessarily ignore causes, even though they may exist? Why? There can be many reasons, and here are some reasons expressed by Henri Poincaré. Henri Poincaré said that we cannot know usually all the causes of an event because the causes are too small, possible, or because the causes are too complex and we don't have enough knowledge for understanding their complexity, or they are very distant. For instance, maybe something very distant, far away in the universe, causes a little disturbance here in this room and can make a huge difference, even though we cannot see the cause because it's very distant. It's just the gravitational influence of a faraway galaxy in the universe. So here are ideas of why there might be causes, but we don't know them. Okay? So this. Another reason, actually, that I like very much is that the causes, and I will tell you more about that in my talk about quantum physics, the reason why we don't know the cause of certain events is because we are involved in them, because we are so closely involved in them that we cannot see ourselves as part of the causes. And in quantum physics, it's the case, because in quantum physics, we cannot completely separate what we do in order to know and what we know. And therefore, we are involved in the process of knowledge, and therefore we cannot know the causes because we are part of the causes. Okay? Now, I told you science needs tests, experimental tests. Is it enough to do a test to truly verify a theory? Namely, say, oh, it's true. This theory is true because it has been confirmed by all the facts. This would be the dream of a scientist, having a true theory that is confirmed by all the facts. But it's not possible, in fact. It's not possible. And the only thing we can do is falsify hypothesis. We cannot check it. We falsify it, according to Popper and according to the history of science. The history of science have shown that, for instance, classical mechanics has been satisfactorily agreed upon by many of the facts that were known, but to a certain extent, to a certain amount of precision. And one day, suddenly, some facts have appeared, some new facts, that have completely wiped out the theory and falsified it. So verification was not obtained. Only falsification of this theory, was really convincing. Okay? Verification was not convincing, only falsification was convincing. And that's why Sir Karl Popper, this celebrated philosopher of science, said that science is not a system progressive towards a final state of certainty. Science can never claim to have reached the truth, okay? Because there is no way to verify, absolutely. But there is only ways to falsify in a very convincing way, okay? But maybe this idea that theories can never be verified, that we can never be sure about theories, is a little bit counterintuitive. Because we have the feeling that when many facts have come in a very good agreement with a theory, we are almost completely convinced. And therefore we say, oh yes, the theory must be true. So, in fact, there are cases in which we are usually convinced. For instance, if the number of predictions of the theory is finite, if the theory predicts only, say, 10 facts, and all the facts are in agreement with the theory, we say, okay, the theory is verified. We accept that. But this is a very special case of a theory. Usual theories predict not only a finite amount of facts, but an infinite amount of facts. So the second case in which a theory could be felt as verified is if the number of theories accounting for the facts were limited. Let's suppose there are only two theories, different theories that predict two different sets of facts. And at a certain moment, you see a fact that falsifies one of the two theories. Then you discard this theory, and only one is left. And this one, you say, it's verified. Fine, I adopt it, because the other one, the only possible other one, is discarded. Okay? But when do you have, when is that you have only two theories possible? It's quite rare. In order to do that, you have to have a sort of previous prejudice of what a theory should be, what we call a logical framework of any theory. And then you say, okay, in my logical framework, only two theories are possible, and therefore I can discard one and retain the other one. But beware, even the logical framework is a hypothesis. And even this logical framework can be discarded in turn. So the idea that you can set a logical framework and then have only a few theories and then discard all the theories but one is very shaky, in fact. I can give you examples. You could ask, okay, there are two theories about light. Either it's made of corpuscles or made of waves. There is no third possibilities because either it's punctual or it's extended. There is no third possibility. Let's check. We test. We say, oh, this experiment discards the idea that it's corpuscular because there are wave-like effects. But this other test discards the possibility that light is pure wave because there are corpuscle-like effects. And therefore, the very logical framework of either wave or corpuscle is not good. So this idea of two theories that are presupposed by a common logical framework is weak also, because the logical framework can be wrong. Okay? You know that in quantum physics, we cannot say that photons are either waves or particles. Probably you cannot say either that the photons are both waves and particles. I will show you that later. But at any rate, the idea that they are either one or the other is wrong, plainly wrong. Okay. Now, in practice, even though a theory is never verified according to Popper, even though it's a case, scientists often behave as if their theories were good, were true. And they need that because their theory is a guide for their research and also a guide for their technological achievements. So even though it's not true in the absolute sense, they retain it and treat them as if they were true. And what are the conditions in which scientists feel confident enough to treat their theories as if they were true? There is what Popper calls corroboration. Corroboration expresses the extent to which a hypothesis has withstood severe tests and has thus proven itself resistant against these tests. Namely, for instance, in modern physical theory, such as relativity or quantum physics, have withstood plenty of tests, even tests against the best of our common sense intuitions. And always, quantum physics have proved better than any other hypothesis. Okay, maybe one day quantum physics will be superseded, but until now it has withstood a number of tests that is absolutely impressive. And therefore, scientists think that the theory has been corroborated. And they use it as if it were true. That's the way it works in practice. Okay? So lack of refutation means confidence. And confidence means that scientists are prone to take the theory as true, at least for the time being. Okay. Now, Popper's idea of science is clear and simple. A theory is never true. It can only be falsified. And when a test comes and falsifies the theory, then the theory is discarded. Here is the very simple idea. But, of course, other philosophers of science have come and said different things. For instance, Imre Lakatos have set nuances to this idea. Because according to Lakatos, who studied the history of science, he said, okay, but look, when there were discrepancies between classical mechanics and observed facts of astronomy, these scientists didn't immediately discard classical physics. They said, oh, maybe we should try to improve it, or to look for new facts more carefully, or to make a new explanation within the framework of classical physics, and so on and so on. For instance, take an example. Normally, according to Newton's physics, the orbit of planet Mercury should be an ellipse around the Sun, a stable ellipse around the Sun. This is the Sun, and this is Mercury. Now, what was observed by the astronomers was that the orbit of Mercury was not exactly an ellipse. It was a little bit different. It didn't make this regularly. It made first this, and then this, and then this, and then this, and then this, and so on. So the ellipse was drifting like that. The ellipse was drifting, and people were saying, maybe there is an explanation within the framework of classical mechanics. And they were looking for another unseen planet that would disturb the motion of Mercury and explain why the planet Mercury was drifting. No one really found such a planet, but no one said, we should abandon Newton's mechanics, because Newton's mechanics was, as Americans said, the only game in town, the only theory that was known. How can we discard the only theory that usually works, but not exactly for some cases? So, before Newtonian mechanics was discarded, one needed a new theory. The new theory came, it was Einstein's general relativity theory of gravitation. And Einstein immediately accounted for the drift of the orbit of Mercury. So people said, oh, that's it. Now we know. We abandon Newton mechanics and we retain Einstein's general relativity. You see, so a theory is not abandoned due to an anomaly. It's abandoned because there is a better one. This is what Imre Lakatos said. Now, what is a phenomenon? You know, I've been a little bit maybe shaky when I said, okay, a theory must be compared to a phenomenon. But maybe you have grasped that a phenomenon, according to modern science, is not something simple. It's not just a perception, a bare perception. It has to be interpreted. For instance, well, this is an example I gave in one of my talks to His Holiness. I walk in the night across the streets of Dharamsala, and I see that the moon is following me. And I claim the moon follows me when I walk across the streets of Dharamsala. Is it a phenomenon, or is it a bad interpretation? That's the point. Maybe I can give a better interpretation of the same observation. And I can say, no, it's not that the moon is moving. It's just that the angle between me, the buildings, and the moon is changing. Okay? So this would be a new statement of the phenomenon. So the phenomenon is already interpreted. The phenomenon is full of concepts, so to speak. That's the point. A scientific phenomenon is full of concepts already, even before it has been compared to the concepts of the theory. So this also shows you that what science is. Science is not a direct inference from perception. It is a huge building of concepts between the theory and the concepts that enable us to interpret phenomena. For instance, Newton, when he said, I want to account for phenomena. What were the phenomena for Newton? Were there just lights in the sky, just stars here and there? By no way. They were highly structured, highly conceptualized observations. In fact, the phenomena of Newton were Kepler's 3 laws of planetary motion, nothing less. Kepler was an astronomer of the beginning of the 17th century, and he observed the planets. And he showed that the planet underwent orbits that had the form of an ellipse. But, you know, the sun around which the planets go is not in the center of the ellipse. It is at one of the two focal points of the ellipse. This is the first law of Kepler. Second law of Kepler, that when a planet moves around the sun, the time it takes for going to a certain trajectory close to the sun is much quicker than the time it takes to go on another piece of the orbit far from the sun. The rule of Kepler was that the surface that is covered by the radius between the sun and the planet in a certain time is the same for the closer part as to the distant part. Here is the, you know, this area must be the same as this one in a definite amount of time. Okay? This is the rule that explains why the planet goes much farther when it is close to the sun, much faster when it's close to the sun than when it's far from the sun. So, and so on. So you see, Newton retained the phenomena that were already conceptualized by Kepler. You understand that observations and phenomena for a scientist, like Newton, are not only perception. They are highly elaborated ideas on top of these perceptions. And, you know, Newton did that. He took his own laws of motion, then he added Kepler's laws, and he derived the famous inverse square law of gravitation. The law of gravitation, namely the fact that bodies are attracted to one another according to the inverse of the square of their distance. So Newton used phenomena, but phenomena in a sense that is much more elaborate than perception. Okay, so I think, well, I have so many other things to say, but maybe instead of going quicker and quicker, I should stop a little bit and let you ask questions, and maybe we'll have occasions to see the further material. Maybe it's better to have discussion, questions, and so on. So thank you very much for your attention. Yes.
You said before, according to the scientific viewpoint, there's no cause when we're talking about the probability, you know, probability. Then what is the difference in probability and prediction? According to the Buddhist viewpoint, there's a cause in when we're talking about the probability or predictions, hypothesis. Then when we're talking on the scientific viewpoint, sort of, why there's no cause in probability?
Okay, as I told you, probability is just a tool for human prediction. So it works as if events had no cause, but in fact, maybe they have cause that we ignore. That's the point. So probability could be, well, could be a reflection of our ignorance about causes, not about the absence, absolute absence of cause. We don't know. In quantum physics, we can use only probabilities. We have no other tool than probabilities to work. So it's very important. And it's very powerful because it works once again. But there is no clear idea about the reason why we should use probability. Is that because there are no causes at all? That would be called indeterminacy of nature. Or is it because we don't know the causes, which would be called uncertainty about nature? Indeterminacy or uncertainty? We don't know. Maybe something in between. I like the idea that it's sort of something in between. It's something in between because we are so much part of nature. We are so interdependent with nature that we cannot disentangle ourselves from the system of causes. And therefore, we are bound to ignore causes. That could be an explanation of the reason why we use probability, even though it doesn't rule out the idea that everything has a cause. So I hope it's a balanced view, I think, of this problem. Thank you.